just check. Okay. So, as promised, today we're actually going to look at lean. Okay. And we are now entering a phase where it's not science, it's skill and the craft to learn how to use this thing. And it can have a bit of an overwhelming learning curve, but luckily there are very good resources for lean. And I had a look at them, and I would recommend that there are particular two, and they're both by Patrick Masseau. One is Glimpse of Lean, which I botched here, the formatting, and the other one is Mathematics in Lean. So Mathematics in Lean is a fairly thorough introduction, which sort of teaches a bunch of things and it teaches you the correct idioms for use. Each proof assistant has its own style, and we're working on lean. So this one is good for explaining how lean works and a bunch of things. And then there is a shorter one also by Patrick, which, where am I? Why do I have all this open? I think I have to close a bunch of these things. Okay. Now I closed too much. Okay. Let me go back. Okay, so this is Mathematics in Lean, and there is a Glimpse of Lean, which is shorter. So this is more like a book. Glimpse of Lean, Patrick says, should take you about 2 to 3 hours to complete. So I will be quite insistent that you actually make progress, because if you don't learn at this point how to actually use lean, you are going to suffer greatly afterwards. Okay. So it's I think the worst strategy here for this course is to postpone, because then you will be kind of left to your own devices in March trying to complete the course that you took in the winter, and you are going to curse the proof assistant. So I will actually want people to report that they did the homework. Okay, so you will either have to explicitly lie to me or admit that you didn't do your homework, or do your homework. I recommend the third option. Okay, so but today I'm going to go through this Glimpse of Lean, which you should then complete on your own time, and also have a look at Mathematics in Lean. So there's a lot of mathematics in Lean here. I think even just like if you go through the first 4 chapters, that's going to take a little bit of your time, but now is the right moment to invest the time, because then it'll be a lot easier afterwards. So we are now climbing on the top of the hill, right? So since this is a doctoral course, I'm going to rely on you being reasonable people who know how to study. So, you know, when I say work through this, you should kind of know which things you want to try out in for yourself, which ones you can just read, and so on. Okay, so let's go through the Glimpse of Lean here, and I'm going to assume that you have a working version of Lean on your laptop with VS Code. If you are an Emacs fanatic, then, well, B1, okay? I'm going to show VS Code as a challenge to all the Emacs fanatics is get all the functionality that you get from VS Code. I think it's going to be hard because they heavily invest into the VS Code interface, and I think the Emacs is lagging behind by now, and seriously lagging behind. Okay, so Glimpse of Lean is a Git repository. I'm also assuming you know how to use Git. If you don't know how to use Git, you must come and talk to me, okay? So it's a Git repository, and I'm going to go from scratch. Well, the scratch is assuming the base assumption is you have VS Code and Lean working. Okay, so you go, you clone it. This is going to take a while, and now, no, it's not, apparently. And now, the first thing you do is, if you look at what you have here, you have these files here, and the main project file is the, is this one. Where is it? What is this? This is some old stuff. So, okay, let's go from the beginning. Lake is the tool that is used to compile lean projects and lean files. So you would normally do everything through Lake, or if you're in VS Code will do it for you. Okay, but let me show you that from the command line, one thing that you want to do is you want to run this thing. It's in the instructions for a glimpse of lean also. What will this do? So the library, this particular Git repository depends on mathlib. Mathlib is a huge library of formalized mathematics. I think it must be the largest one available out there. And we are going to rely on it. It's what makes Lean actually a serious mathematical tool. So this library, the Glimpse of Lean wants it, and it's pretty large. And so if you try to compile it yourself, then it's going to take a while. Even like on my Mac Studio, it's unpleasantly long. It's longer than one coffee break. So you don't want to do that. But Lake can fetch precompiled stuff for you. And this is the first thing you do. You say, Lake, get me all these things. Now, they have a bit of a Node.js philosophy, which is in every folder, we're going to install every dependency that you ever need. So eventually, if you work on this a lot, you're going to have 12 copies of mathlib. But the assumption is that you don't care because you have 1 petabyte of disk, and who cares, right? And nothing's going on. I have a backup copy already installed if this fails, if this step fails. What am I on? No, they should work. Well, okay, we'll let it work. So this is going to download all of mathlib. It's surprisingly not doing anything.
Mine said it was total 216 megabytes.
Yeah, it's 216 megabytes, yes. But I mean, you know what this is like. This should be.
School internet is quite weak.
I thought I was on the special faculty network that you can't access. Yeah. Ah, yes. But apparently, there we go. Yes. So once you get this, then we're gonna start. I'm going to wait. Okay. In the meanwhile, we can look at the repo directly here and see what's going on. Okay. So by the way, you might be tempted to run this like not on your computer in some virtual environment somewhere. Okay, but really you should just run on your computer. Okay, is like that's why you have it. It's not a remote terminal. It has a CPU that can be used. So there is a first file here called introduction. Let's see how are we doing here. No, we're done. Okay, so now it downloaded stuff. It happily reported the number of milliseconds this took. So it's not too bad, even on this network. And so now I'm going to open this in VS Code, which is what you want to use. And now it's confused because it thinks this is the old version of it. Okay, so let me open something. So the first thing you should open here is introduction. So in the file, so this is the general layout of a lean project. So you have various files, the ones that we're going to come back to that. We're not going to do that now, but I'm going to show you now first how this thing works. Okay, so when you open this, you're supposed to, I closed it, but lean info view, here it is. So it's supposed to open, it's going to open like this. Where is my, so here. There we go. So there is something called lean info view, which I get with Command Shift Enter, and you probably, whenever I say command, it's probably control for you for Windows people or Linux people. So when you work with a file like this, you're going to have two windows. There is the source code on this side, and then there is the interaction on the other side. So this is an interactive tool. And when you see red, that's when you should be worried, because that means it's not compiling. and it's right now it's complaining. So there is a restart file button, which often helps. When it's yellow, that means it's compiling. If it's compiling for a long time, it might be that you are trying to compile all of mathlib, in which you should not do unless you let it compile and then you go out for a walk or something. Now it's not yellow anymore, so it's happy. Sometimes this will disappear for you and then you will not know how to come back. So first of all, as a general rule in VS Code, control, or I will keep saying command, but map it to control. Command Shift P is your friend because it gets you the commands for VS Code, and this has a search. So if I start saying info view, it says toggle info view, and it's Shift Command Enter. And this is good to remember. Shift Command Enter turns it on and off. Okay. The other one that's good to know is Command B, which turns on and off the file explorer if you're on a small screen. The only reasonable way to work with Lean is to have a screen that is wide, really, really wide, like the one in my office. Okay. And then it's really nice. A laptop is maybe a bit nasty, but it's still doable. You will see, but it's much nicer on a wide laptop. I'm going to do this, and now I'm also going to turn on the line wrapping because these lines here are too long and we don't see them. It says here this is Command Z or Option Z, which doesn't work for me for some reason. It just creates a question mark. So, but Command Shift P is my friend because as I can say wrap and it just tells me. There you go. Now it's wrapping. And we're going to go through this file together. Let's see. Command. Oh, maybe that's what it was. No, this is now Command. Oh, Option Shift Z. No, it's just doing more strange things with. Yeah. I probably have a key binding done some other way. It doesn't matter. Okay. So stuff that starts with dash minus is the green stuff is the comments, and the comments start either with dash minus or single line comments start with double dash. Okay, so here we have first some definitions. By the way, underneath, Lean is going to translate all of this into very basic type theory, right? And that's a process that we are not looking at today. But just keep in mind that there's some sort of translation going on and it's fairly complex. Why am I saying this? Because you will sooner rather than later experience errors regarding the translation process, and then you have to know that that's what's going on. Okay, so let's see. First we have a definition. A definition starts, maybe I can do this. I don't know, my screen is too small. So first I have a definition. If you can't see well, you can turn off the lights. I don't know, this is visible. So this is a definition of what it means that if I have a sequence U and a real number L, that U converges to L. And this is just the usual definition. Let's read it. For all epsilon greater than 0, there exists an n, such that for all n greater than equal to n, the absolute value of un minus L is less than equal to epsilon. First of all, this is completely standard mathematical notation, which is very good. Okay, we don't have to write like JavaScript looking code or some nonsense like that. Notice the form of the definition. The definition has a name, the thing we're defining. Then it has some parameters here, so U and L. Then it has a colon, and then it has the type of the definition. Prop is the universe of propositions. So we are defining a proposition as opposed to a number or a function. You don't have to provide this, it'll compute it. Okay? But it is informative and usually useful to write down the type that you're trying to get, because that helps also with all kinds of mechanisms and it makes Lean understand you better. So this is just the standard definition of what it means for U to converge to L. Okay? Next, we have another definition here, which is continuity. So if you have a function f from R to R and x0 in R, what does it mean that f is continuous at x0? And it's still completely the standard definition. For every epsilon, for every positive epsilon, there's a positive delta, such that whenever you have a x within delta of x0, then f of x will be within epsilon of f of x0. Okay, now how do people type all these things? So if you put the cursor on any kind of symbol, it'll tell you information about it. So for instance, here it tells you that this is actually typed also. The actual name for this is real, and apparently this blackboard R is just some additional notation, and it's a type, okay? And there is documentation, and it tells you where it came from, what import statement you would need to get this thing going. So it would be mathlib data.real.basic, but we are not importing that because we are importing glimpse of lean library basic, which probably imports a bunch of things here. You see, this is base. This is so it got imported indirectly. So the other thing that is very useful is this bottom line, which tells you how to type it. So it's telling you that you can type the blackboard R by either \r or \br or \real, but there are lots of options on how to type it. How do they type this arrow? I put my cursor on the arrow, and then I see, okay, a bunch of ways to type the arrow. So this is useful. Even these subscripts, they will tell you how to type them. Okay. So this is a definition, which just means we're defining a notion. We're not actually proving yet that any particular f is continuous. So we now have two notions: what it means for a sequence to converge, what it means for a function to be continuous. Here's something that you learn in your analysis class very early on. Let's read this. Okay, so now we see that apart from a definition, we can have an example. So an example is just something you want to show, but you don't want to give it a name. So then you say example. So then you see the name is missing. I don't have to give a name. And I just start listing parameters. I say, suppose f is a real valued function. Suppose u is a real sequence of reals. Suppose x0 is in R. And now the first strange thing happens here. Let me try to give you which one was it? Yes, okay. The first strange thing happens here that we might not be used to is we here say suppose u converges to x0, and what is strange about this is that we're naming it. Okay, so we're saying let hu be the hypothesis that u converges to x0. In a formalized mathematics, everything gets named. Well, I mean, they try hard to avoid naming everything, and they're quite, because it's not usual in ordinary mathematics to name every hypothesis that you have. Usually just you wave your hands and you say by the hypothesis, and even though there are 7 hypotheses, you think that people will guess which one you meant because there's like one that makes sense. And in fact, there is a tactic precisely for that in Lean, and it'll guess which one you meant. But when you're making a statement, it is not uncommon that you name this. If I didn't want to name it, I could write it like this, and now I didn't name it. But it's common to name everything. So the objects that you're dealing with and the assumptions. Okay? Later we will see ways of not naming assumptions, but right now we're naming everything very explicitly. So we have the assumption hu that u converges to x0, and we have the assumption hf that f is continuous, colon. So what is the type we're going to inhabit? And so now we say we're going to produce an element of this type. So what is this? Well, this is the type or proposition, right? We discussed this, types, propositions, same thing. Okay, so this is the proposition that f composed with u, which is a sequence, right? It's the sequence u mapped with f, that it converges to f of x of 0. So in other words, continuous maps preserves limits of sequences. Okay, now you say colon equal, and now what you are asked to do on this side is provide an element of the type. So now I need to provide an element of this type. So if I explore what it is, sec limit, it's this here. So I could try to write it down directly. I would start by saying, so I would start to say function, which takes an epsilon and the assumption that epsilon is positive, and then it needs to do something to produce this n, and so on. There are proof assistants that work this way, ACDA in particular, where you do this all the time. We could do this in Lean, but it is not idiomatic. It is idiomatic in Lean to heavily use a different mechanism called tactics. Tactics are like commands that they're not actual elements of types. They're commands that instruct Lean how to create the element in question. So in particular, because we're constructing an element of a proposition, and all elements of a proposition are equal, we don't care which element we're going to get. So it is idiomatic that when you have a proposition, you use tactics, because with tactics, it is easier to get things done, but you have less control over what was done, because you have intelligent tactics that just work on their own and they do something. But you don't care because you will never look at this proof of the proposition. If we were constructing a natural number, then we would presumably care which number we have and we wouldn't use tactics. Okay, so the way you start working on a tactic is with the keyword by. Once you go into by, you will see it'll go into tactic mode. So I need to turn on the info view now. Eventually learn the keystroke. There we go, the info view. Maybe I tried the default. Is this still large enough for you? Yeah, okay, because otherwise we're not going to see anything. So here we're now going to start to see things. Okay, let's see. As I move my cursor, as soon as I go into by, it jumps to tactic mode and it tells me what is going to be done. And the way you read this is the context. This stuff here is the context. So we have one variable f of this type, we have one u of this type, we have this. These are the things available to us. Why are they available to us? Well, because they are the parameters to the example. And we need to produce an element of this type here. That's the goal. So now we say, ooh, how are we going to do this? And there are now several dozen tactics that eventually you learn how to use, and each proof assistant has its own. So you can read this stuff later at home. So for instance, there is unfold, which will unfold the definition. So as soon as I move deep enough into this, you see, it's unfolding it. So now you say, aha, it's a for all statement. So how do you prove a for all statement? Well, logic and sets, first year course, yes? You say, let's suppose we have an epsilon and suppose it is bigger than 0, okay? And that's tactic intro, or intros. So you say intros, and this is actually two assumptions. It looks like one assumption, but it's two assumptions. So we say two assumptions. The first one is that we have an epsilon, and the second one is some assumption about epsilon. And at this point, as I moved here, notice the difference. Here, I have for all epsilon greater than 0 exists n. When I do the intro, I have just the exists n. And this is the general strategy. You try to break down your goal into simpler and simpler parts until nothing's left, and then you're done. That's the general idea of how you do these things. And there are lots of ways to getting to the end of it. But intros is one of the most common things you will ever do. It's you just say, oh, I'm proving something, I will get extra assumptions, now I do the rest. I don't have to do both of them. I could do one of them, you see, but then it would still have one left, namely that epsilon is greater than 0. So apparently, oops, this notation, where am I? This notation, for all epsilon greater than 0, this is just an abbreviation. This is actually a notation for all epsilon in real numbers. If epsilon is greater than 0, then all the things I try to teach in logic and sets. Okay? So we have this, and now we have to produce an n. So how are we going to get the n? I really, really highly recommend that when you're working with the proof assistant, that you keep your mathematical brain turned on. It's very easy to turn it off and say, oh, I will just use tactics. It's going to work. Well, it's going to work for the easy stuff like intros, and then at some point you're going to get to actual math. So now you have to tell me, well, how do we prove that continuous maps preserve limits of sequences? What would be, where are we going to get this n from? How would you prove this? So we need a capital N. So I'm looking here. I'm looking at the goal. We need a capital N such that for all n, little n greater than or equal to capital N, the sequence, so f of u of n is with the, minus f of x0 is less than epsilon. So I think the first step should be probably, because we have an epsilon, we should be able to do something useful with continuity of f, right? So somehow we know that continuity of f can give us a delta. We give it an epsilon, it'll give us a delta. So let's have a look at that. What this says here is that if you give me, let's read this type theoretically. Type theoretically, this says that an element of this type is a function which takes an epsilon and a proof of the fact that epsilon is positive, and then it's going to give me an element in here. What is an element in here? Well, an element in here is going to be a delta, a proof that delta is positive, and all this other stuff that comes after it. Okay, so how will we now do that? Here, I have the assumption that HF is an element of this. So HF is a proof of for all epsilon something, something, something. The way you use such an assumption is, because this actually is a function, is you just apply it. So for instance, I can say, HF applied to epsilon. If I do that, look at what cow is now. Cow is, if epsilon is greater than 0, then I'm going to get then you will get a delta greater than 0 such that blah, blah, blah. But so now I say, oh, okay, so if I apply just epsilon, I will get something that is still a function and it wants the fact that epsilon is positive, but I have that. It's called h epsilon. So now the cow says there exists, now I have an assumption, there exists a delta such and such and such. So now I would want to get my hands on delta. Still logic in sets. I have an assumption that is an existential. How do I use it? Well, I introduce a new variable delta and satisfying this, and I keep going. All of that is done, because this should be easy because we will be doing this all the time. All of that is done here with this thing here, obtain. So let's read this line. This line here is, this thing here is what I wrote earlier. So this is h of f, continuity of f, applied at epsilon and the fact that epsilon is positive. Hello. And then it's going to be in 3 parts. It's going to give me a delta, the fact that delta is positive, and it's going to give me the rest. Here, Patrick wrote down what it will be, its type. But in practice, you wouldn't. You would just do this, okay? Because it knows what the type is. So when this happens, then let me show you the difference between this line and this line. If you say let, this obtain is like a fancy let. It's kind of like let, but it allows you to write patterns here, which is why we're using it. So I don't really want this assumption. I want this assumption that is already broken into parts. And the parts are delta is greater than 0, and whatever it satisfies. So instead of having this line, which just gives me a monolithic assumption called cow, I actually write this. How do I know that I can write this? Oh, here is a trick. This is an important trick. You might think that you see parentheses here, but you don't. Okay? This throws off people. These are not parentheses. If I hover on this thing, does it say what it is? This is triangular parentheses. This is triangle left and triangle right, not the round ordinary parentheses. And you type them using backslash less than and backslash greater than. These guys are super useful. You can use them whenever you have some multi-part thing and you just want to give the parts or get the parts, you use this, okay? So I know that there will be 3 parts. Why do I know there will be 3 parts? Because I looked at what my cow looked like. So the way I would write this in practice is like this. I would say, oh, I know I want to use HF at epsilon. So I would actually first just say obtain blah blah. I can actually do this. Obtain blah blah h of f of e. I say I want this. Then I look at it and I say, ooh, this is made of parts. I want to take it apart. How do I know it's made of parts? Because I have experience in reading this. So I say it's an existential, so it's going to have 2 parts. But actually it's going to have 3 parts because it's an existential with an additional assumption that it's greater than 0. So then here I write backslash less than delta pos hf. Okay, once I see what I will get, then I write the pattern. Unless you are a robot, then you write the pattern before you see what you're going to get. Okay, so now we have the 3 parts and we go on, okay, and we say what? Okay, so what? So what do we have now? We have a function, we have a sequence, we have a point. We know that u converges to x0. We know that f is continuous. We have epsilon, it's positive. We have delta, it's positive. And we have this assumption. For every x at r, if x minus x0 is less than delta, then f of x minus f of x0 is less than epsilon. Okay, now we want to get our hands on our capital N. Well, we're going to use the fact that u converges to x0 somehow. And so the story pretty much repeats here. And I will delete this because nobody would ever write this in practice. Okay, this is just to inform you of what is going on, right? I will bet you anything that Patrick copied this thing in after he saw what it is. Okay, he did. Patrick, if you're listening to this, I am betting you a lunch that this is what you did. Okay, so here. So it's the same story again. Now we apply HU, which is the fact that u converges to x0, to delta, and the fact that delta is positive, and you're going to get 2 parts, a number. Let's call this number m, okay? Let's call it m. It is, again, we're doing logic and sets, first year. Do not confuse bound variables. Evil, okay? This is what was going on. The n, we're looking for an n here, which is a bound variable. So we shouldn't have another n anywhere because it's going to confuse children in the kindergarten, but also like general population and even mathematicians. So no, I want to call it m. Okay, so what I have? Now I have a number m, and I have the assumption that for all n greater than m, u of n minus x0 is less than delta. So I'm making progress. And now I say, oh, but now I know now I have an idea what is the n I'm looking for. It's m. So how do you tell when you're trying to prove that you have an existential statement? After you have read this tutorial and mathematics in lean, you will know that when you have an existential statement, the sort of the standard way of proving it is to say, oh, I will tell you what the n is. And that's the use tactic. So now I say use. Well, what is it going to be? It will be just this m. And then it says, let's have a look at how it changes. So it says, you need to prove that there exists an n such that blah, 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 blah. So I say, well, yeah, we're going to use m. And so now it says, okay, then you have to prove that for every n greater than m, see, it's just keeping track of what I'm doing, such that blah, 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 blah. Okay? But now I have a for all. Whenever I have a for all, I can be on autopilot and say intros, because that's going to give me more assumptions. It's always good to have more assumptions. By the way, what is the best assumption to have? False is the best assumption to have. If you can get your hands on the assumption that says false, you can then prove anything you like. Okay, so, some people say it would be a disaster for mathematics if somebody proved false. Well, on the other hand, we could just prove anything we liked after that. Okay, so here we go. So we do an intros, and it's going to be an intros of two things, because it's going to be n and the fact that n is greater than m. So they're introing two things here. Okay, and my list of things is growing, and now I have to do this. Okay, so now let's stare a little bit at this. Okay, I'm asked to prove that f composed with u of n minus f of x0 is less than epsilon. Now, actually, by the way, if I do simplification, simp, then this composition becomes f of u of n. So that's easier to see. Now, what could I do? Well, one thing you can do is you look at what is available. So what is available? The stuff that is here in the context is available, and also 100,000 theorems in the Mathlib library. So maybe we have to use one of those 100,000 theorems. Job is going to work on how do you figure out which theorem to use. But it's a serious problem. It's a real problem. But right now we don't have to do that. We can use one of the assumptions. So it's this one that is going to help us. How do I know it's this one? Look at what the conclusion of HF is. The conclusion of HF is that f applied to something minus f of x0 is less than epsilon. The conclusion is like the thing I'm trying to prove. I have a matching epsilon. I have matching f of x0, except this x here, x, instead of x, I want u of n. So I want to use this one. So to use this one, you use the apply tactic. You say, I want to use this. So what will happen? Okay. So let's think about it. Suppose somebody tells you, oh, this thing here follows from the assumption HF. Are you done, or do you still need to verify that you can actually use the assumption? You have to verify that you can actually use the assumption. So what will that mean? Well, first of all, you have to tell me what to plug in for x. You have to tell me that in here, I should be plugging in u of n, right? But then I'm not done. Then I also need to verify that u of n minus x0 is less than delta. Only then can I use this assumption. But the way that this works in a proof assistant is slightly backwards. What you do is you say, I would like to use HF, and then it will tell me what needs to be checked. Okay? So I would like to use HF. Let's see the difference. So here, I go here, boom, and now something happened. It wants, okay, so it could correctly guess that x needs to be un. How did it do that? The machine was staring at this conclusion, just like we were, and at this thing, and it was wondering what to plug in for x. And it could tell, because it's pattern matching, and it says, oh, x appears here, whereas here, u of n appears, but you can't see that because I deleted the simp, right? So it could figure out that x is u of n, but it didn't figure out why this is true. So it remains to be proved, okay? How do we prove this? Well, that's the conclusion of HU. You see, it's the conclusion of this one. Yeah. So we want to say apply HU. Presumably they will say apply HU. Okay. There are two ways to do this. I could say apply HU, and then it would say, why is n greater than m? And I would say, oh, well, I have it. But they did something else here. They said, I will tell you exactly what it is. Look. You can always do this. You say, I want to use HU. I want to use HU. This is for any n. Okay, I want this n. By the way, this n here is different from the n that you see at the bottom. If you're confused about this, you're like normal people. You're confused about bound variables. Okay? Only logicians and computer scientists are not confused about bound variables. Everybody else, including normal mathematicians, is confused. So if you're confused, come talk to me. We'll have a psychotherapy on bound variables, and then you'll be fine. So this n here is different from that n here. Okay, so we're going to apply HU with this other n applied. Okay, and I'm looking at what I'm getting here, down here. Let's call it cow so that I can. Okay, so I say, oh, cow is, if n is greater than m. Oh, but I have n is greater than m. It's hn, so I will provide it, hn. Oh, but now cow is the exact thing that I want. Okay, But if it's the exact thing that I want, well, that's the exact tactic. You say, I want exactly this. And I'm done, and I have my first theorem. Okay? Questions. You should be asking lots of questions. If like there's a little detail that you're worried about or that went too fast, please raise your hand and ask. So what did we find out? We found out, yes?
I have a question.
Sure.
Somewhere in the step between, I don't remember exactly when, the program did some pattern matching.
Yes.
How often is it wrong, if ever?
Oh, so when it was here, when we said that it wants that we need to use HF, it was able to tell that this X here needs to be U of N. Yes. Okay. So this is first of all, it does this all the time. Okay. Why does this do this all the time? Because then if it can do it successfully, you don't have to tell it what to do, right? You can just say, oh, use that theorem, and it'll figure out by itself how to use the theorem, or at least the parameters that it can figure out. That's less work for you. Okay. And then whatever is left is left. Okay. So the question is, how often does it go wrong? Actually, it doesn't go wrong. It either does it, or it says, I don't know how to do it. It'll say, I don't know how to apply this theorem because I can't find things. And then maybe you have to say it more explicitly. But this particular way of applying typically does not lead you astray. It's not going to go down some sort of blind alley where you have the wrong thing and then you have to realize, oh my God, the machine found the wrong pattern. It happens in a different spot called type classes. You can mess it up. Type classes is another way. So there are lots of mechanisms for guessing what the user wants. So this one is just sort of straightforward pattern matching. This one is not so bad. Type classes can go wrong. And the way that one goes wrong is you're working with a set that is a group, but the machine knows that there are two possible group structures on this set. They might actually be the same group structure, but it found it in two different ways, okay? And you think you're working with one way, but it thinks it's working with another way. Even if they're equal, it's going to create confusion at some point.
These type classes are in the same way Haskell has.
Yes, these are type classes a la, well, they're more like a la Coq, but yeah, also a la Haskell, yes. Yes, we'll come to them, not today. Okay, so where do we go from here? Now it says you should go and solve these exercises. Rewriting if and only if for all exists. So these are just some basic exercises. And I see no better way to make progress than to do the exercises. It doesn't matter how I philosophize here in front of you, okay? We have to do. So I suggest we're just going to go through the exercises, but you will tell me, okay? So first we have a break. Okay, so if you go to Split Naučilnica and then you go to do the course, you're going to get resources. One is the video recordings. Another one is whatever I do in class. Okay, first two lectures, whatever I did in class, the PDF. Yes. And course notes here. Okay, it's not a book. I'm not going to write the 10th book on Lean. That's stupid. Okay, I don't have the time, nor do I have the expertise to do it because the Lean developers know how to do it. Patrick did a very good job, and others. There's also, it's not the only one. Okay, so here you have sort of a summary of what happened in every lecture and what you should be reading. Okay, with links to videos. So where is it? Again, it's repeated here somewhere. Discord. Maybe I'll have to link it. I will link my plan, which apparently I forgot about, is here it is, video and the class notes. I will link every lecture is going to have at the bottom the things that happened in that lecture. But what you have is what happened and what you should be doing. So you should be installing Lean 2 weeks ago. Okay, so this last week, you should have played the natural numbers game. Okay, this week you should be completing the exercises and then read a large chunk of mathematics in Lean. For instance, you could do it before you fall asleep every night. See how long it takes you to fall asleep. Does it put you to sleep or does it keep you awake? So maybe it is just one sleepless night and you will know all of Lean. Okay, break. Okie dokie. So let's go on. So this is the first exercise. It's called rewriting. That's because this is written for mathematicians. Mathematicians like to calculate things and say equal, equal, equal. This is equal to this, this is equal to that. And so there are specialized tactics for proving chains of equations and stuff like that. If you didn't have them, anytime you wanted to prove that A equals B with 3 intermediate steps, you would have to use the transitivity property of equality until you like die of boredom. So there are better tactics than that. Okay, so one that is going to be very useful to anybody doing any kind of algebra is called the ring tactic, because it allows you to prove simple identities that are true for the operations of plus and times and minus. So ring, what you normally call a ring. So here's an example. Let's read it. So if I have 3 real numbers a, b, and c, then a times b times c equals b times a times c. Okay? So let's see how this is going to work. We go into the tactic mode. Now it says you have up here, you have A, B, and C, and you need to prove this equality. By the way, you see how it's using parentheses on the right hand side, but it's not using them on the left hand side. That's because in the notation of Lean, star is declared to be a left associative operation, which means when there are several consecutive stars, if there are no parentheses, it is assumed that they are on the left. And this sometimes is not so clear when you look at something you're proving and there are parentheses missing, and then you're like, oh, which way are the parentheses? The way you discover which way the parentheses are, you place your cursor, your mouse, on the star. If I place it on this star, it shows me that this star will bind together A and B. So now I know that these two are in the parentheses. If I put it here, you see this star. So again, I go here, I get everything. This means that this star is binding together the C and also the A cross B. So this is how you can discover that what it is that you're binding. Can your Emacs do that? Okay. And for something that's like this, associativity, now we could look for a lemma that says that the real numbers are associative, and then we would apply that lemma. Okay, 100,000 theorems, one of them is the right one, but the tactic ring will just do it. And it says, no goals, done. Yes? Let's see what ring found. If we do this, if we name this cow, then we do it. Now I can say, print cow. So it found something. Let's see what it found. So this ring tactic did the following. It said, okay, the result is a function which takes a, b, and c, and then it does this here. It applies this function to this stuff here. This is the proof it found. Okay? Is there a fastest proof? Is there a faster proof? Yes, probably we could try to use the mathlib. The way you would use the mathlib here is you would say apply question mark, and then you would hope that apply question mark will look at all known theorems. This is the one you're trying to improve. It will look at all known theorems, and then it'll suggest which ones might be useful for the purposes of solving this. So it'll say, oh, you could try to write refine x in blah, blah, blah. No, I'm not going to write that. Okay, you could try this, you could try this, you could try this. Is there an apply? Okay, I don't like any of these refines. Is there an apply? Give me a reply. Okay, it's suggesting a gazillion things. This time is not particularly useful. Okay, it really wants to. If you know, mul ek, mul f, div ek, div. But it's just associativity, stupid machine. Surely associativity of the reals is a known thing. Okay, so there's a lot of work to be done, yes. Ring comes to the rescue. There are other better ways of finding this tactic, but the ring associativity. One thing that you learn eventually is you say, I think I know what it's called. It's mal underscore, and now I press control space, and I say, this one looks good. Then I put my cursor here. No, I click here, and then it tells me what it is, except I still don't see anything. So I say, what the heck. Now if I put my cursor here, does it say? Yeah, now it does. Okay, it says A cross B cross C equals, no, it's down here. It says if you have G and it's a semi-group, and then ABC equals, this is what I want. What do you mean you don't know how to apply it? Okay, it doesn't know how to apply it. You asked earlier about patterns, but now you're playing with your phone, so you will never find out. It doesn't know how to get A, B, and C. So maybe if I tell it what the A, B, and C are, nah.
No, because this isn't associativity.
This isn't associativity? A, B, C equals A, B, C, B, A, C. Oh, sorry, I'm not proving associativity. Sorry, misread it. A, B, C, B, A, C. Thank you. Okay, yeah. Okay. The point is, ring is what you want. Okay, so the way this tutorial looks is first they show you what to do, then they tell you do that. Okay, so here we have a plus b squared is a squared plus 2ab plus b squared. Does ring work? Yep. Okay. This is just so you can remember what ring does. Okay. Now let's do something more interesting. Am I not? How do I have to wrap? Go. Let's do the next one, which is I have 4 things. So these are all going to be very silly things, but we'll learn how to use these. Okay, so I have 5 numbers, and I know that A equals B plus C, and I know that B equals D minus E, and I have to prove that A plus E equals D plus C. Okay, what the hell? Okay, so what is this? So first I see that I could get rid of A, and I can get rid of A, and then if I get rid of A here, I will have just B plus C, and then D is going to be, so maybe I want to get rid of A. So the way you want to get rid of A is like this. Okay, so you're staring at this, and you say, I want to plug in my goal, this A, I want to replace this A with B plus C. That's called rewriting. You have a known equation, and you want to replace the left-hand side with the right-hand side in your goal. That's RW for rewriting. You give it a list of things to rewrite. So I'm going to say rewrite using H. What it's going to do is it's going to find A and replace it with B plus C. There, see? It changes to B plus C. Okay? And then I say, what would I like to do now? Oh, let me also replace B with D minus E. So another rewrite, but H prime. So now, okay. So now if I stare at this, I see that E should cancel out on the left. So I will be left with D plus C equals D plus C. Now it's time for the ring tactic. This is just some basic calculation. Ring tactic, we're done. You don't have to do consecutive rewrites like this. You can do several of them in a single rewrite. The cool thing here is the following. As I do my rewrite, observe this. I do H. I will now move my cursor by 1, and A will be replaced. And it's showing me already what the first H did. And then I go on, and now I know what the second H is. Why is this useful? This is useful because the way I would actually produce this proof in practice is I would say, oh, I want to do a rewrite. Okay, I want to do a rewrite. And I say rewrite, but rewrite with what? And then I say H. And it's telling me this is what you got. And now I look at this and I say, oh, I also want to do B. I want to replace B using H prime, so I can just keep going. And as I'm writing down these rules here that they should be rewriting, I can see interactively how far they got. I don't have to do the following. Rewrite H, move the cursor all the way here to see what happened, then go back, do a little more, then move the cursor all the way there to see what happened. No, it's just, okay, somebody programmed this thing the way it should be. Okay, and then ring. Okay, we're just lucky that we're working in a ring. I think it probably works for semi-rings, I would imagine, not just rings. Who knows? Okay, here's an example. You tell me what to do. Let's learn the best tactic ever. It's called sorry. Whenever you don't know what to do, you can just say sorry, and it'll say, well, okay, you're sorry, we're done, but you're sorry. This is not finished. So if you use a sorry, the thing you're doing will be underlined with this wiggly yellow thing. So that means you were sorry there. You have to, yes. But it's useful because it allows you to, you don't have to do your proofs in a linear fashion. You can have any order in which you want to program, and maybe you want to state them but not prove them. And then, so one thing that often happens is the following. I'm trying to prove theorem A. I'm in the middle of the theorem A, and I see that I need lemma B. So I go in front of theorem A, and I write down lemma B. But I don't prove it yet. First I say sorry. Then I go back to my proof, and I use the lemma. So to make sure that I wrote down the lemma that I actually want. And once I see that it's actually the right lemma, then I will invest the time into proving it. So that would be a typical use of sorry.
Have to be above the...
Yes, so it doesn't know about any identifiers that are defined below. It's not mutually recursive.
Okay.
Unbridled recursion a la Haskell is unacceptable, because as soon as you have unbridled recursion and you can just do any recursion you want, then you can immediately prove anything you want, because you prove false with the proof P, which is equal to P, because that's just recursion. In Haskell, you can actually have a definition that says let x of type A equal x, right? If you try to evaluate it, it'll just go, it'll cycle. But it will type check. But since it type checks, that means it's a proof of something. Okay, so that's why we very much don't want a recursion that isn't guaranteed to terminate. We only want recursion that is guaranteed to terminate. Okay, what to do? Well, it actually says you should use the assumptions H and H prime. You see, this is where you would normally turn off your brain, right? Your brain wants to say, don't think, just write this. You will be done. Just write this. It's gonna work because it's a simple tactic. Okay, maybe not. Let's see. We have to think. Okay. So we're gonna do some rewriting. Which one do you want to use first? Do we first use H prime or H? Your brain says, don't think, just try both possibilities. Done. We can do this without thinking. Excellent. Well, if you find yourself in this situation, you should be asking yourself, why is the brain running the tactics? Why isn't Lean running the tactics? Okay. But yeah, you should rewrite H prime first so that you get both B's in, so that then the both B's become the D's, and then you have 4 D's. Okay. Let's try another one. Let's just go through this. Here's another one. Now it's something more interesting. We have 3 real numbers, and we want to show that this is the exponential function. So e to the a plus b plus c is e to the a times e to the b times e to the c. Now, this we cannot do without MATLib library, because we need to know how exp is defined. By the way, if you want to know how exp is defined, you put yourself on exp and you press F12, and it'll take you to the definition of exp. And it says, when you do this, You are entering a special land called professionally designed library of formalized mathematics. There will be layers and layers and layers of stuff. Let's try to see how deep we have to go to figure out what exp is. Okay, the exponential of a real number x is a real number, which is exp of x dot re. Okay, so apparently this exp here inside is a different exp. This is not recursion. The inner one is different. It's a complex exp. Okay. So what they're saying is that the real valued exp is defined in terms of the complex valued x. So let's look at what the complex valued x looks like. Okay, the complex valued x is of a complex number z is cosec lim x prime z. Okay, this we're going to guess it has something to do with the limit of a Cauchy sequence in a complete ring. Okay, and x prime is the Cauchy sequence consisting of partial sums of the Taylor series of the complex exponential function. Let's look at it. Oh, it's up here. Why is this? What is this? Okay, if z is in C, we're going to define a Cauchy sequence in C with respect to what norm? With respect to the absolute value. So what we are noticing now is that a concrete thing such as exponential function is defined in terms of very general constructions, because we're now working in a complete ring, which is complete with respect to the given norm. So this is becoming, it's backwards. You have to be a third-year student to understand this first-year stuff, how it's built. This is a general phenomenon. As a general rule, it is easier to formalize more abstract things. This is maybe counterintuitive, but if you think about it, it really isn't. The more abstract it is, the easier it gets to formalize. In a way, because there's less than you can do. You know, it's so abstract, you're kind of forced to do the only thing you can. Yes? You seem unhappy?
Mathematicians go up a layer of an abstraction, then they need to rewrite based on more.
That is a very good point. Each time they go up the layer of abstraction, do they have to redo everything? Yeah, pretty much. Luckily, they climbed the abstraction ladders a lot slower than they designed these libraries. So, 20 years from now, people will say, oh, we can't believe that we were not using homotopy type theory from the beginning. So they will have to redo everything. But then they will have to re-implement the proof assistance also. So it's a bigger problem. But yes, it's a good observation. Another problem with this is that if you proceed from abstraction and then you go to concrete, that makes it hard for students. Because now, how do I explain this to a student? The student wants to understand how the exponential function is defined, and I say, consider a complete ring. What? What is a complete ring? So it gets nasty quickly. Okay, so this is some partial sum, right? It's the sum, m is in the range of n, z to the m factorial. Now it is what you think it is. Notice, let's practice. Notice how these are not parentheses, but the triangular parentheses. Okay, it's barely visible. Why am I saying this? Because more than once I had a lot of fun debugging my own code because I had the wrong kind of parentheses, like 2 hours. And then somebody would say, hey, why don't you have the triangular parentheses there? And I said, okay. So, but it's two things. You see, it's not just the sum. This is the sum. These are the partial sums. But here, there is a proof of something. And if I hover, it'll tell me what it is. It's is cosec. This is getting kind of out of hand here. Okay, but it's something. It's a proof of the fact that this thing is Cauchy. It's up here. You see, it's up here. It's a proof of something. Okay, enough of the rabbit hole. Let's climb out. You climb out with control minus. So this is maybe not very intuitive, at least it's not to me. To go to the definition, you press F12. To go back where you were, you press control minus. Actually, it makes sense. Control minus is more general. Control minus just says, go to where you came from. But there might be various ways of going forward. Maybe I go to a definition, maybe I do a search, maybe I switch to a different bar, I open a file, Control minus just says, go where you were. Go where you were, go where you were, go where you were, we're back. Okay, this was the exponential function. How do we prove this? Okay, they gave us a hint. They told us that there is a thing called exp_add. If I hover on exp_add, it tells me that it says rexp of x plus y equals rexp of x times rexp of y. Now, first of all, this seems weird. This is rexp, but I have exp, and they're calling this lemma exp. This is exp, and now suddenly there is a rexp. Well, we can hope that this rexp is actually the same thing as our exp. Who knows? Okay? Now, there's the fuzzy way of doing this is here you say, oh, I am not going to worry too much. It's a tutorial. Probably it's going to work. The other one would be go and investigate what rexp is. That would be another way. Okay, so exp_add. Now, how do we do this? We want to rewrite. Which way do we want to rewrite? What's the goal? Let's go in here. This is our goal. So we want to rewrite this rexp. Which way are the pluses? It's a plus b in parentheses and then plus c. See? A plus b stick together. So now I need a rewrite rule. So if you want to see what you want, so here's one way to do it. You say like this, and you say, okay, exp_add is this thing, but now I want to specialize it. Cow is this thing here for all x, y, blah, blah, blah. Which x and which y should I be using? And you look at down here and you say, oh, I want x to be a plus b, and I want y to be c. And now if you look at cow here, it says x of a plus b c equals x of a plus b times x of b plus c, which is looking promising. So this is the thing I want to use. So if I'm here in the middle of a rewrite and I'm trying to write down how to rewrite, maybe I don't know how to rewrite off the top of my head. I first go and I explore a little bit to construct the equation that I want. So cow is the equation that I want, you see? This one is the one I want. And now I could say rewrite cow. Because I got it. I produced the one that I wanted, and now I have it, and it's going to work. But that is not idiomatic. That is silly. So instead, what you do, once you discover what it is that you want, you plug it directly into this rewrite. You delete evidence that you didn't know it off the top of your head, and you show this to people, and they say, he's so smart. Okay? He can just write these things down. And now we repeat the story. We just need rexp of a plus b. So once I did this, I know now it's going to be exp_add ab. And I'm done. I don't even have to do ring. Because rewrite is smart. You don't have to explain, in fact, how to use exp_add. Let's repeat the same thing again. I can just write exp_add. And when I write exp_add, it found the first opportunity. Let's be careful. It found the first opportunity from left to right, this one to rewrite. It figured out by itself what x and y are supposed to be by doing pattern matching, and it did it. And now I see that there is another opportunity, so I tell it, just do it again. I'm done. Now we are being smart. Okay? This is better. And this is actually doable immediately. This is something you could directly write. This one is hard to write directly because you have to explain what the x and the y are. Here you don't have to explain. The machine is intelligent. Okay, exercise.
I have a question.
You have a question.
In the natural number game that we
Yes.
saw, there was a repeat
Yes.
of things. Could we write?
Let's try. Repeat means keep doing this tactic until you can. And when it doesn't work anymore, then stop. Yep, it works. Yes. There will always be infinitely many ways of using the tactics. Yes.
So put the repeat inside the brackets, I think.
Oh, really? That's getting like this? Oh, it doesn't like this.
I'm remembering it right.
Yes.
It's working on a tactic.
It works on a tactic. Yeah. There are constructions that combine tactics into fancier tactics, and repeat is one of them. Okay, here's an example. It's got a sorry, let's get rid of it. So maybe we read the instructions. Let's do an exercise. We have to prove that exp of a plus b minus c equals exp of a times x of b divided by x of c times exp of 0. And because there are 100,000 theorems, they told us which ones to use. They told us, why don't you use exp sub and exp 0? So now suppose somebody says, somebody gives you a hint. So exp, you're supposed to use exp sub and exp 0. Well, you know, my brain wants me to not think. Am I done? Am I done? Ring. Not done. Okay, I have to think. Okay, let's think. So, first of all, what is this exp sub? I try to use it. Did it do something? Before it, I had exp of a plus b minus c. Afterwards, I have exp of a plus b divided by exp of c. Okay, so this seems reasonable. Yeah. Okay. I can also hover on it, and it'll tell me what it is, and it's what I expect it to be, and it's also written in the comment. Okay, so then I say, how about if you use x0? So I'm almost there. Let's compare the two sides. One is exp of a plus b divided by exp of c. The other one is exp of a plus b divided by exp of c times 1. I just need the multiplication by the unit. I have to get rid of this times 1. And the instructions tell me what to do, because this is a beginner's tutorial. It says, why don't you use mul1? Okay, I will use mul1. There we go. No. Are we done? We're not done. Why are we not done?
You're missing one exp.
I'm missing an exp-add. Oh, they want me to use exp-add. Okay. Does it matter where I put it? Oh, I'm done. So the natural numbers game, a lot of it was like this, right? This kind of stuff. Okay. Rewriting from left to right. Okay. You also learned this in the natural numbers game, that if you have an equation which is backwards, then you use this arrow. How do you type the arrow? You hover. It tells you can type this arrow by typing \L or \left arrow, which I hope nobody types, or \L minus for some reason. Okay, all of these. Okay, let's go to the interesting bit, which is how you would really do this kind of thing. It's calc. Calc is the thing you really want. So you will often be faced with some sort of equational type reasoning, and it also works for inequalities, by the way, where you want to prove something, but you want to do it in steps. You want to calculate. So you want to start with the left-hand side and then do one more step, one more step, one more step, one more step, and get to the right-hand side. That is very common. There is a tactic for that. It's called calc. And the way you do it, you just write these, you start by writing, okay, left-hand side. Okay, we're going to go there, left-hand side. We have to start with CE. And then we say where we're going to go. We're going to go to this equals b times a minus d. So before we look at the proof, just observe the form. It says c equals this. And then the next step is that this thing here that I wrote, I should actually put it down here. And I can. I could copy this here. I think, yes. Huh? But that's silly, because now it's there, now it's copied. So it's just there twice. This is just cognitive noise. So the tactic allows you to put an underscore here, because there is precisely one thing that could possibly be here, which is that. And then if you put an underscore, it will figure it out. Oh yeah, you meant that. And so you go c equals this equals this equals this. Okay, how did they do this? And so now in each line you have colon equals, and then you have to prove the thing that is required for you to be proved. So here they say you're supposed to prove that c equals b times a minus d. And h actually says C equals B times A minus D. So they say by rewriting using H. But I think I could just say H here. I don't see why I have to do rewriting. H. Yeah, it's just H. It's literally H, right? So I'm here, it says, why is B times A minus D equal to 0? Oh, that's, oh, sorry, I'm already past it. I'm here. Why is C equals B times A minus D? Why isn't it showing me? I think it's confused about what needs to be done. It's just still, it doesn't know that I'm here. Does it know now? It doesn't, yes. No, well, now because of an error. Okay. Anyhow, either rewrite H or just H would work. And then this one is probably literally H prime, is it? Or do I have to? No, this one I have to rewrite. So I find some proof of this step. Here, this could be several lines. You know, it can start to spread. This is not just very short ones. And then the last one, why is B times A minus A times B 0? Just, I'm sick of this ring. Okay. This is a very useful device. So let's do this one together. Okay, first of all, what do we need to do? We have the assumption that A equals B plus C, and we're supposed to show that x of 2A equals x of B squared times x of C times C squared. Okay, doesn't seem too hard. Let's go. So the way, okay, right now, is there another exercise? Yes, there's another exercise. Okay, so this one told us what the steps are. The next one will not tell us what the steps are. So let's do the one where we already know the steps. So the first step is x of 2A equals x of 2 times B plus C. By what? It's not literally H. Is it H or is it rewrite H? It's going to be rewrite H because it's not exactly H. Okay. Then the next one wants me to prove that 2 times B plus C equals B plus B plus C plus C. Help. How do I do that? Yes, but you will have to be more specific than that. Yes, maybe there are some hints. No hint. Any ideas? Ring. No goals. What? It worked. Okay, good catch. Also, how about simp for simplify? No. Oh, simp did something, you see? It got rid of exp 2 times. Before simp, we had exp. After simp, we don't have exp anymore. Ring. Okay, next. Why is exp of B plus B plus C plus C exp of B plus B plus C plus C?
We defined that before.
Yeah, we had it somewhere. What was it? Exp? Add, I think it was. Rewrite? Rewrite. Okay. I get weird line breaks. Okay. This is just weird line breaks. So if I could do this, but it's kind of small. Is this too small for you guys? Okay. We really need the better screens. Yeah. So a screen that works for me, it costs 450, I think, something like that. If it cost 900, then it would be, then I couldn't see the pixels, but you know. Okay, there we go. Next one. I want to show that x of b plus b times x of c plus c is x of b. What is that? Let's see. X and x and. There you go. Next one. Right? Why not? Because ring presumably knows that xb times xb equals xb squared. Cool. Now you tell me what to type. Calc. What was this? Calc, and then they want me to indent by 2, and now I start writing. And now it says, I'm confused. Okay, well, let's go see here. What is it? What is it that I need? I start with C. Okay, C equals.
Is the indentation working?
Yes, yes. The indentation, it's indent. It relies on indentation, and you can also not rely on indentation, but Haskell style, I think, using curly braces and semicolons. If you don't want to rely on indentation, but indentation is heavily used. C is equal to what? What's going to be our first step?
D times A plus B.
Okay. By what? Why is this equal to D times A plus B? Do you want it to write just literally H? H. Okay. Ah, what does it say? Light bulb. Generate a calc block. Sure. Okay. Next line. The previous line is equal to what? What do you want the next step to be?
Replace B with A times D by H.
So I will get what?
D times A
Plus
A times D.
by?
The D is wrong.
By?
Rewrite H.
We're done? No, we're not done. We still need, we still have to get to the end. By the way, it's showing us what we need to do. See? So we say equals. So what is this line now equal to? What do we want?
2 times A times D.
And that will already be what we want, right? 2 times A times D. By ring, you think. There you go. Yeah. Okay. No, ring is good, but there are better ones. Simp is magic. Simp works all the time, everywhere. Okay. Let's see.
Equal size.
I manually align. What is the question?
The previous examples.
Yes. This seems to be more idiomatic, right? Don't do this, do this. Yeah.
We don't plan to do it.
It seems like people who designed Lean also know how to use Haskell, because it's idiomatic in Haskell to align stuff like that. Okay, that was 0, 1 rewriting. Then you have if and only ifs. And then you have this, and then you have this. So for this week, I would like you to go through all of these. This was really not that complicated, by the way. We just did a lot of talking as we went along. But I would like you to do all of these, and then there are some topics here. Where are the topics? There are solutions here. Okay, now it turns out that if you give undergrads exercises and solutions, they're still too young for that kind of trick. But you are all master students and PhD students, so you will, of course, not look at the solutions, right? Where are the topics? Here, exercises, topics. What are the topics? Logic, if you like logic. Things like, it actually defines propositional calculus as an inductive type. Okay, this is now more advanced. Galois junctions. This is order theory. So if you like order theory and infima and lower bounds, there's something like that. Intuitionistic propositional logic, and this was classical propositional logic. Okay, similar. And rewriting. What kind of sequence limits? So this is just more sequence limits. Things like A is less than A plus B. Okay, by linearith. It teaches you linearith. Let's read one of them to see what kind of things are in here. What is this extraction business? This is a really, really silly way of saying that phi is monotone, strictly monotone. Okay, for some reason, it's called extraction. If phi is monotone, then for every n and n prime, there exists an n. greater than n prime, such as phi of n is okay. So this is saying if phi is strictly monotone, then it will go above any value. It's unbounded. Okay, if anybody does this exercise next time, please explain to me why this is called extraction. Cauchy sequences. So here, I would like you to do the basic exercises and seriously attempt one of these, okay? So don't worry if you don't get to the end of it, but make an honest attempt and see how far you get. This is also to gauge the difficulty of what we're doing, so you will have an idea of what's ahead of you, okay? That's it for today. So, homework. It's fun, it's addictive. It's not really homework, it's a drug.